Here are a few questions from the paper mechanics. All are 40 questions. We may go through them one by one. What is meant by a wave function? The wave function denoted by psi of r comma t is a mathematical function that depends on the spatial coordinates x, y, z and time t. It represents the complete information about a physical system. Therefore, wave function is also called as the state function. Give the physical significance of wave function. The magnitude of the wave function is higher in areas where the particle is more likely to be found and lower in other areas. Say this is a wave packet. Inside the wave packet, a number of waves are present. The entire wave packet may move with one particular velocity called group velocity. Velocity of the particle is equal to group velocity. The particle is likely to present where the amplitude of the wave function is maximum and the probability of finding the particle is small in the rest of the places. The wave function can be real or complex, but the probability density is always real. Say psi is a complex quantity, psi of r comma t equal to a plus ib. Then psi star is a minus ib. Probability density p of r comma t is psi star psi, that is absolute square of psi, which is equal to a minus ib psi star into a plus ib, which is equal to a square plus b square, a real quantity which is free from I. What are the conditions that a wave function must obey? The wave function must be single valued. For the given values of x, y, z and t, psi is having only one value. The wave function must be finite everywhere. The wave function must be continuous and its derivatives are also continuous. If psi is the wave function, dou psi by dou x is continuous. Dou square psi by dou x square is also having some value. The wave function must be normalized. That is psi star psi d tau is equal to 1, which is normalization condition. What is meant by normalization condition? The probability of finding the particle is given by the formula absolute square of psi, that is psi star psi. Suppose the condition psi star psi d tau is equal to 1. This condition is called a normalization condition. According to the probability interpretation of the wave function, the probability of finding the particle within the volume element d tau is expressed as absolute square of psi into d tau. Since the particle is undoubtedly within the volume element, the integral of absolute square of psi into d tau over the whole space must be unity. What's the importance of normalizing a wave function? Suppose a wave function is unnormalized, that should be multiplied by a constant called a normalization constant. Once the wave function is normalized, that will provide definite eigenvalues. The amplitude of the wave function is arbitrary. It is because the Schrodinger wave equation is linear and it can be multiplied by a constant of any arbitrary magnitude. The wave function so obtained remains a solution of Schrodinger wave equation. After normalization, the amplitude of the wave function has a fixed value. Give the orthogonality condition. Suppose psi m and psi n are the two wave functions and are mutually orthogonal, that is perpendicular to each other. They should satisfy the condition. The product of one wave function with the complex conjugate of another one should be vanished in between minus infinity to plus infinity or a to b, two conditions. If this condition is satisfied, then psi m and psi n are mutually orthogonal. or psi m star psi n dx equal to 0 is also acceptable one. If these conditions are satisfied, another one condition is psi m star psi n dx equal to 0. Then the wave function psi m and psi n are said to be mutually orthogonal. Give the orthonormal condition. Psi n is a normalized wave function, that is psi n star psi n dx equal to 1. Then psi m is also normalized wave function, psi m star psi m dx equal to 1. The eigenvalue of psi n is En. The eigenvalue of psi m is Em. They are different. Em not equal to En. These two eigenfunctions are supposed satisfying this condition, psi n star psi m dx equal to 1. For n equal to m, then this is called a normalization, normalized orthonormality condition. That psi n star psi m dx equal to delta nm. If n equal to m, the integral value is 1. If n not equal to m, the integral value is 0. And the two wave functions are orthogonal to each other. If n is equal to m, they are orthonormal. This is normalization, orthonormality condition. What are stationary states? The states for which the probability density is constant in time are called stationary states. Consider a wave function psi of r comma t, that is equal to psi of r e power minus I e n by h cross into t. Actually, this is psi of r comma 0. The value of t is 0 here. E power minus I e n by h cross into t. This is our psi of r comma t. Then psi star of r comma t, which is equal to psi star of r comma 0 e power I e n by h cross into t. This minus I is changed as plus I. Then p of r comma t, which is equal to psi star of r comma t into psi of r comma t, which is equal to absolute square of psi of r comma 0, because e power minus I n by h cross into t into e power plus I n by h cross into t equal to e power 0. Anything over 0, 1. So psi star psi, that is absolute square of psi of r comma 0. This is a constant. What is meant by observable? Observable refers to a quantity that is obtained through the process of observation or measurement of a physical system. These quantities are always real entities, such as rest mass or the charge of an electron. Could you also clarify what an operator is? An operator is a mathematical quantity that, when applied to a function, can transform it into another function or keep it the same. Here, d by dx is a differential operator. If it is operating on sin x, we can get cos x. The operator changes the function sin x into cos x. Allow the same operator to operate on e power imx. We can get im into e power imx. The same function we can have. This is eigenvalue. This is eigenfunction. What are linear operators? An operator A is said to be linear if it satisfies the following two conditions. A into alpha f is equal to alpha af. Here alpha is a constant. Operator A is operating on f plus g. A into f plus a into g. Now we can call this operator A as a linear one. What are commuting operators? If two operators A and B are commuting with each other, then AB minus BA equal to 0. This is 4 into 3 equal to 3 into 4. What do you mean by a Hermitian operator? A linear operator A represents an observable quantity is Hermitian if it satisfies the condition of psi star A psi d tau equal to A psi whole star psi into d tau. You may write psi comma A psi which is equal to A psi comma psi. The psi means psi star. A psi is in Ket space. Then A into psi whole star is A psi in Bra space we have written. Prove that the eigenvalue of Hermitian operator is real. Operator A operates on psi, gives one eigenvalue A into the same function psi. This is called an eigenvalue equation. Multiply both sides of equation 1 by psi star from left and then integrate. Psi star A psi d tau equal to psi star A psi d tau. If small a is eigenvalue, take it out, you can get equation 2. That means psi star A psi d tau equal to A into psi star psi d tau. From the condition of Hermitian operator, psi star A psi d tau equal to A psi whole star psi into d tau. But A psi is small a into psi. Put here small a psi whole star psi into d tau. Here psi star A psi d tau equal to A star psi d tau. From these two equations, A equal to A star. Eigenvalues are real, mere numbers. A equal to 5, then A star is also 5. Suppose A equal to 5i, the value of A star is equal to minus 5i. Here A not equal to A star. So that if you consider the eigenvalue is imaginary, we won't say A equal to A star. But eigenvalue is real, we can say A equal to A star. Therefore, this condition is satisfied, this is not satisfied. All the eigenvalues are real as far as the Hermitian operator is concerned. Prove that the eigenvalues of a Hermitian operator corresponding to two different eigenfunctions are distinct and that the eigenfunctions are orthogonal. What they expect is A is a Hermitian operator and is allowed to operate on two eigenfunctions, different eigenfunctions, psi and pi. The eigenvalue produced by A when it is allowed to operate on psi is small a. When A operates on pi, it can provide the eigenvalue B. A minus B not equal to 0, which means that A not equal to B. A and B are different. And we have to prove psi and pi are mutually orthogonal. That means pi star psi d tau equal to 0. See here, this is eigenvalue equation. A into psi equal to small a into psi. A is Hermitian operator. When it operates on psi, gives eigenvalue A. Here A is an Hermitian operator. When it is allowed to operate on another one eigenfunction pi and gives eigenvalue B. These two are eigenvalue equations. Now pre-multiply equation 1 by pi star and then integrate. We can get pi star A psi d tau equal to A is a constant. Take it out. Pi star psi d tau. Now we have to apply the condition of Hermitian. If A is Hermitian, pi star a psi d tau equal to a pi whole star psi into d tau. Substitute the value of a pi equal to b into pi. So we may write b pi whole star psi d tau. That is b star into pi star psi d tau. But b star equal to b. Eigenvalues are always real. B star equal to b. Therefore b into pi star psi d tau. Now find out the value of equation 3 minus 4. The left hand side pi star a psi d tau. In equation 4 also the left hand side is pi star a psi d tau. So the result is 0. If you subtract b integral of pi star psi d tau from this, you can get a minus b into pi star psi d tau. Here a minus b not equal to 0 because a and b are different. The value of a is not equal to value of b. Therefore pi star psi d tau equal to 0. If pi star psi d tau equal to 0, then pi and psi are mutually orthogonal. Can you demonstrate that when two Hermitian operators commute with each other, their product is also Hermitian? Let us consider that a and b are two commuting Hermitian operators. Then their product is also Hermitian. If psi 1 and psi 2 are two wave functions, we can construct an integral psi 1 star ab psi 2 d tau. If a is Hermitian, psi 1 star ab psi 2 d tau is equal to a psi 1 star b psi 2 d tau. Again, if b is Hermitian, a into psi 1 star b psi 2 d tau is equal to ba, see here, b into a psi 1 whole star psi 2 d tau. We know that ba equal to ab. So ab psi 1 whole star psi 2 d tau, because a and b are commuting with each other. Ba equal to ab or ab equal to ba. Hence we can write psi 1 star ab psi 2 d tau is equal to ab star psi 1 star psi 2 d tau. Consider this one as c. Psi 1 star c into psi 2 equal to c star psi 1 star psi 2 d tau. C star psi 1 star psi 2 into d tau. Therefore, if a and b are commuting with each other, then the product is also Hermitian. AB is also Hermitian. See this problem. If A and B are Hermitian operators, show that AB plus BA is Hermitian. Now we have to work it out. See here. Psi m star AB plus BA psi n into d tau, which is equal to psi m star AB psi n into d tau plus psi m star BA psi n into d tau. Just we have separated in two intervals. If AB is Hermitian, then there is B star A star psi m star psi n d tau plus A star B star psi m star psi n d tau, which is equal to, see here, A star B star plus B star A star and psi m star psi n d tau. This is AB plus BA whole star psi m star psi n d tau. Taken is psi m star AB plus BA. Consider this one as C. Then C star, if this is Hermitian, AB plus BA is Hermitian, psi m star C psi n d tau equal to C star psi m star psi n d tau. See here, AB plus BA is C star is AB plus BA whole star, then psi m star psi n d tau. Therefore, AB plus BA is Hermitian. In the same manner, we cannot prove AB minus BA equal to 0. AB minus BA is Hermitian. AB plus BA is Hermitian. But AB minus BA is not Hermitian. What is expectation value? Most of the time we can get a particular result called expectation value among the many measurements we made on a single dynamical variable. Expectation value of an operator A is psi star, then operator psi into d tau divided by psi star psi d tau. Suppose the wave function is normalized, the value of psi star psi d tau equal to 1. Therefore, expectation of A for normalized wave function, expectation of A equal to psi star, then operator value psi into d tau. If you want to know the expectation of Px, x component of momentum, you can write psi star h cross by I, operator value. X component of momentum is h cross by dou by dou x psi into dx. The x component. If you expectation of E, if you want to find out the value of expectation of energy operator, psi star IH cross dou by dou t is energy operator value into psi into dx. This is the energy operator. If you want to know the Hamiltonian operator, psi star minus h cross square by 2m del square plus v psi into dx. This is a value of here we should put d tau because x, y, z. See the 19th question. State Ehrenfest's theorem. According to Ehrenfest's theorem, when studying the movement of a wave packet related to a moving particle, quantum mechanics will produce the same outcomes as classical mechanics if you use the expectation value of relevant dynamic quantities. The quantum mechanics provides the same result as provided by the classical mechanics. Here, expectation of Px equal to m into d by dt of expectation of x. We know that momentum P equal to mv. The classical result equals the result arrived from quantum mechanics. State the principle of uncertainty. In general, expectation value of an operator A is psi star A psi d tau. Suppose the wave function is normalized. Then A square is equal to expectation of A square equal to psi star A square psi into d tau. When we measure the observable A once, we obtain a single value. However, if we measure A multiple times with the system in the same state, the average value of all the measurements can be represented by expectation of A. This is average value. The uncertainty delta A in the measurement of an observable A, that is error in measuring A in the state psi, is defined as the square root of, this is square root, difference in the average value of A square average value, and the square of the average value minus, difference is minus square of the average value of A, average value of A square. See here, average value of A square. This is square of the average value. This is our delta A, error in A. State Heisenberg's uncertainty principle. When observing an atomic system's motion, measuring certain pairs of physical variables with accuracy and simultaneity is impossible. We cannot measure the two variables at the same instant of time. When attempting to record a quantum particle's position and momentum, it is impossible to simultaneously measure them with complete accuracy. If the particle's position is measured first, there will be some error in calculating its momentum. Anyway, the product of errors must greater than or equal to h cross by 2. Here, delta x is uncertainty in error, uncertainty in position, that is error in calculating position. Delta p is then error in calculating momentum. H cross is h by 2, Planck's constant by 2. What are canonically conjugate variables? There are certain pairs of variables such as position, momentum, energy, time, and angular momentum angle that are known as canonically conjugate variables because they do not commute with each other, but they may give canonical commutation relation. We know that the value of x comma p equal to I h cross. To prove this, find out the value of x comma p into psi. That is equal to xp minus px into psi. This is x into h cross by I dou by dou x minus h cross by I into dou by dou x of x entire is multiplied by psi. This is equal to x into h cross by I dou psi by dou x minus h cross by I into dou by dou x of x into psi. Two variables. This is x into h cross by I dou psi by dou x minus psi into h cross by I. Take this psi. Dou x by dou x is 1 minus h cross by I x into dou psi by dou x. Say x h cross by I dou psi by dou x. This is h cross by I x into dou psi by dou x. Cancelled out. You can get minus psi into h cross by I. This is equal to I h cross into psi. X comma p into psi is I h cross psi. Therefore, x comma p inside the square bracket is equal to I h cross. What do you mean by a Hermitian operator in terms of matrix aspect? If A, the given matrix is Hermitian, then if you take the conjugate transpose, that is A dagger. If A dagger is equal to A, then A is said to be Hermitian. Prove that the given matrix 0 minus I 0 is Hermitian. Here, this is sigma y, Pauli spin matrix. 0 minus I 0. Then sigma y star. Complex conjugate of this sigma y is 0 I minus I 0. Then make the transpose of this matrix. Sigma y star transpose is 0 minus I 0. We can get the original matrix sigma y. Therefore, the given matrix is Hermitian. What are Bra and Ket vectors? The Bra and Ket notations originate from the term bracket with the letter C removed. Write on the letter word bracket, B-R-A-C-K-E-T. If you remove the letter C, we can get Bra and Ket. Put the parenthesis, this bracket, then drop the letter C. Take a segment, we can get, this is Bra space, the remaining of is Ket space. This is Bra vector, this is Ket vector, this symbol. The state vector psi is expressed as Ket of psi. The state vector psi star is expressed as bra of psi. Operating on a ket vector by an operator from left will provide another one ket vector. Say A is an operator. From left we are operating on ket vector A. We can get another one ket vector A star. Operating on a bra vector by an operator from right will provide another one bra. Complex conjugate of a ket space is a bra space. Say ket vector with a star is bra vector. The same case is true for complex conjugate of a bra space is a ket. Say this is bra of psi. If we take the complex conjugate, we can get ket of psi. The normalization condition in Bra and Ket notations are given below. Psi star psi d tau. The psi star is expressed as bra of psi. Then the psi is expressed as ket of psi equal to 1. What are eigenvalues and eigenfunctions? A function f is called an eigenfunction of the operator A. If when the operator A operates on the function f, we can get the same function multiplied by a constant c. A into f is equal to c into a. This is called eigenvalue equation. The constant c is called the eigenvalue of the operator A. D by dx of e power imx equal to im into e power imx. This is the example for eigenvalue equation because the same function e power imx is obtained. Consider the second equation d by dx of sin x equal to cos x. This is not an eigenvalue equation because the function is changed. Sin x is changed into cos x. What is a unitary operator? When operator u satisfies the condition u dagger equal to u dagger u equal to I, then the operator u is called a unitary transformation operator. What is Hilbert space? Hilbert space is a linear vector space. Hilbert space has an inner product operation that satisfies certain conditions. Conjugate symmetry. Here psi 1 is in bra space, psi 2 is in ket space. If interchange psi 1 and psi 2, we can put a star. Psi 2 in bra space, psi 1 in ket space with a star is equal to psi 1, psi 2. Linear with respect to second vector. Psi 1, comma a psi 2 is present plus b psi 3. See here. Psi 1, comma a psi 2 is in bra space, but b psi 3 is in ket space. This is equal to a into psi 1 psi 3 plus b into psi 1 psi 3. Antilinear with respect to the first vector. Here a and b are taking in the complex conjugate form. A is in bra space. If you take it out, is a star psi 1, comma psi 3 plus b star psi 2, comma psi 3 because a and b are present in bra space. If you take them out, a star and b star are their values. Then positive definite. Consider a wave function in bra space and the same wave function in ket space. That is equal to absolute square of psi. What is Schrodinger representation? In Schrodinger representation, state vectors psi are time dependent, whereas the operators are time independent. That means psi changes with the time. What is Heisenberg representation? In the Heisenberg representation, state vectors are time independent, but operators are time dependent. In the interaction picture, both state vectors and operators are time dependent. Prove that x comma px power n inside the square bracket is equal to n ih cross px power n minus 1. Say x comma px power n is written in this form: a comma b c px power n minus 1 comma px equal to px power n. Then align the terms using the formula. See here, this is a, this is b, this is c. Is a comma c into b. Here c into A comma B. Then x comma px is our IH cross. IH cross px power n minus 1 plus this px. Once again, this x comma px power n minus 1 is returned in terms of x comma px power n minus 1 into px, because px power n minus 2 into px equal to px power n minus 1 n minus 2 plus 1, which is equal to px power n minus 1. A power m and a power n equal to a power m plus n. Once again, use the formula. It is a comma c into b plus c into a comma b. You can get this relation. Then x comma px is our IH cross. If you multiply this px power n minus 1 into IH cross, here px into x comma px power n minus 1. If you carry out the operation using the same logic, x comma px power n minus 3 into px, once again you can get another one term, IH cross px power n minus 1. In this way, n times we can get IH cross px power n minus 1. Therefore, x comma px power n is equal to n IH cross px power n minus 1.